Good afternoon and welcome to this Aberdeen Area Committee event. We've got a rather long-winded title, but it says pretty much what it says on the tin. It's a practical approach to life extension and integrity risk management in offshore wind foundations using structural monitoring with Robin Price. First of all, I'll introduce myself. I'm Steve Cromer. I'm a Fellow of the Institution of Mechanical Engineers. I'm Chair of the Aberdeen Area Committee. I'm also Chair of the Upstream Oil and Gas Committee in Aberdeen. We are actually being recorded, so if you want to review this later on, you'll be able to go onto the IMechE site and review it. It's a good time for us to look at this. I was looking at the BBC News, and the Seagreen wind farm has just started. It's fully operational. 114 giant wind turbines in Scotland, which is going to produce 2/3 of the Scottish demand for households. So the wind farms are out there, and we now need to look at how we monitor the structures. So during this presentation, if you have any questions, there is an attendee question box which you could open up. If you could type your questions in there, or any other issues you may have, type them in there and we'll deal with them at the end. We'll get a good look at that. So without any further ado, I'd like to introduce Robin Price. He's a CEng and a member of the Institution of Mechanical Engineers. He's a senior mechanical engineer at the engineering consultancy Arup. He also manages the development and deployment of Arup's cloud-based offshore wind life extension and asset management platform, which has the acronym LEAP. Robin, are you in there?
Hi, Steve. Yes. Can you hear me okay?
I can hear you perfectly.
Brilliant. I'll crack on then.
Absolutely.
So thanks, Steve, for the intro, and to the IMechE for giving me the opportunity to present today. My name's Robin Price, and I'm a senior mechanical and structural engineer at Arup. I'm chartered with the IMechE, and I specialise in structural integrity. A large part of my work is currently around the asset management of offshore wind substructures. As Steve said, it's a booming business, both in Scotland, the UK, and globally. And so that's the focus of my session today. But I'm hoping that a lot of the themes are kind of relevant and applicable to your work in other types of offshore structures, and indeed onshore structures like bridges, onshore wind, and so on. So I've introduced myself just to give you a quick recap of the company I work for, in case you're not familiar with what we do. Arup is a global firm of over 18,000 designers, engineers, consultants, and technical specialists. We work in more than 140 countries across the world, and we have a long history in the energy business. We have over 1,800 people specialising in that sector. And whilst we work in other parts of energy, in offshore wind, our business has supported a large number of projects and developers across the whole asset lifecycle. So from planning and design through to asset management and operations and maintenance support, which is more what I'm going to talk about today. So as Steve said, the title's quite long, but just to sort of break it down a bit into chunks, I'm talking about approaches to extending the life of assets and managing integrity risk, and how we can achieve that by using structural monitoring. So a good place to start is addressing the question of why monitor structures in the first place. I'll give a very high level overview of the concept of design lives and fatigue loading, and then followed by a summary of sort of common approaches to structural monitoring and what's currently out there. And then I'll go for a sort of deeper dive into Arup's solution to this. We call it LEAP, our life extension and asset management platform. And then I'll finish off with a couple of case studies. So one is some recent work at the London Array offshore wind farm, And then I'll touch upon some other applications in other industry areas just to wrap it up. And then, as Steve said, there'll be time for questions and answers at the end. So why do we need to monitor the health of structures? I think there's a few key reasons or benefits to doing this. One is that monitoring allows us to measure a given metric in near real time. This allows us the opportunity to alert us when exceedances of certain threshold values that might concern us have been reached. We can also identify trends, and with some analysis we might be able to give an early warning of developing risks. We can also use it to validate designs in terms of measuring the in-service values of design assumptions. This is something I'll come on to later. We could also optimize operations or justify increasing performance, such as applying extra loading or upgrading, in the context of offshore wind, the control system, so maybe extracting more power from the wind. And also, in the event that defects or integrity risks are identified, or even just for routine maintenance, we can use monitor data to support analysis that might be able to justify reduced inspection and maintenance campaigns. So we might be able to target certain certain areas of the structure, saving money, time, reducing personnel risk. And finally, kind of the crux is that all of this together can allow us to justify continued operation in the event that we've exceeded some sort of design assumption or found an integrity risk, or we can possibly demonstrate life extension, so extending beyond the original design life. This is something that's very much of interest, both in oil and gas, offshore wind, and other industries. So that's some of the value, just to give a bit of perception from sort of the owners of assets, so maybe the client side. There's a few issues with managing these large assets in a challenging environment. Wind farms are huge assets. Unlike single installations in other parts of the energy industry, offshore wind farms contain hundreds of assets spread quite far apart, and maintenance can become quite challenging for these, especially if you have to inspect every location without any targeting. And there's also decreasing confidence in design assumptions as the asset ages, if you can't replace it with true data or monitored data, because you have to rely on either limited inspection data or what you assumed at design. And there's also an increasing interest to extend the life of assets, and these targets can be quite challenging. Newer designs are very optimized, so it gives you less margin, for or less headroom in the design for exploiting additional life. So I appreciate I might be preaching to people who are very familiar with this, but just to give a bit of context, we're primarily talking about fatigue driven assets. So although this approach of monitoring the condition of structures is not exclusive to fatigue loaded structures, it's a particular value in the case of offshore structures to be able to monitor fatigue load. So these are structures where the safe operational life is driven or governed by fatigue. For offshore structures, this is predominantly wind and wave loading, but also for other structures, there are other sources of fatigue loads. So, for example, for bridges, we might have wind, traffic, we might have operational loads that can contribute fatigue damage over time. As a bit of fun, I thought just sort of consider what we really mean by design life. These structures are very, very old, thousands of years old. Can we say that their design life has been exceeded? They're still standing, but they're not in the same condition as they were when they were built, and arguably not fit for purpose. So in the context of this talk, and when we talk about life extension or extending design life, we're talking about codified periods of time which a structure is considered fit for purpose and also safe for operation. And in codes of practice, that's typically defined with a probability of failure during that time period that is tolerable. And it's therefore not necessarily how long the asset lasts until it ultimately fails, but how long it can tolerate the design loads and its intended service function with an acceptable level of reliability. So for offshore structures, particularly offshore wind foundations, the design is governed by fatigue load. For a wind turbine, that's a combination of wind loading, so thrust of the turbine, and also wave and current loads on the substructure. So you see that in the diagram on the left. And that is to say that during the operational life of the structure, it will see many millions of cycles of fluctuating load, a bit like the time history in the middle. And whilst these load cycles are not large enough themselves typically to cause global failure of the structure, they can propagate cracks or defects in the structure, and these might initiate fabrication defects, stress concentrations such as welds, and ultimately they will reach a size that could lead to failure of the structure. At design, we approach this by using relationships such as SN curves, there's an example on the right, which use test data to determine the allowable number of load cycles that will result in failure with a certain target reliability. For complex load histories, like shown in the middle, in real structures, we need to use numerical techniques to break that down into cycles or load cycles of certain magnitudes, so that we can then kind of construct the damage using an SN method to calculate the number of cycles or time period overall that would lead to the structure reaching its design life or fatigue sort of limit. And at design, we don't know exactly what that real load history will be. It will be different at different parts of the structure. And so we have to make assumptions which will be conservative about the loading and also other parameters which influence fatigue load or crack growth. And that kind of brings us on to monitoring. So the question really is, for structures which are fatigue critical, i.e. governed by the fatigue loading that they might see, if we can measure that load history in service and evaluate the real loading on the structure, we can therefore gain a more accurate prediction of the fatigue damage accumulated by the structure. So modern structures, be it in offshore wind or other industries, are more and more commonly instrumented with some level of data gathering. And I've listed a few common ones. Now, this may not be with a view to achieve the results I've been discussing, fatigue, load assessment or life extension, but just generally to monitor the condition and have data available. So we have things like operational data from SCADA systems, so that's recording operational metrics, environmental conditions, wind speeds, and so on. Strain gauges have long been used in steel structures to measure very local measurement of strain, so elongation of the steel, and from there it is possible to evaluate the local stress and therefore load in the structure where the sensor is placed. We also can measure the dynamics of the structure, so we can use accelerometers to measure the motion in time. And then there's other kind of offshore, maybe specific data sources, so measuring sea states and wave heights using wave radar. We might measure displacements or inclinations to sort of track the slippage of a grouted connection maybe over time. And then we can also measure other things like temperature or humidity or salinity. There are all sorts of other metrics that we can measure which may allow us to characterize the condition of the asset over time. But for life extension, to assess the fatigue loading of the structure, we're interested in primarily monitoring loads. I've got an example of a monopile foundation wind turbine oil screw, which is perhaps a nice sort of simple structure to illustrate the point, but the principles apply to other structural types. We need loads at fatigue critical locations in order to make the analysis and assess what the fatigue damage would be with monitored loads. And the traditional approach is to use strain gauges, which, as I mentioned, measure load at a very local position where the sensor is installed. And so the typical approach would be to install strain gauges at many elevations. Critical elevations tend to be below the waterline, even below the mudline, and that kind of restricts where you can place them, and it's a very challenging environment. And you also need a lot of sensors. If you imagine more complex jacket type structures, to install strain gauges at all critical locations would be very difficult, even prohibitive. And so Arup looked to kind of solve these issues for our clients, and to provide a data system that could act almost as a digital twin for offshore wind foundations. So providing the right data to deliver insights into fatigue utilization, and also to support ongoing asset management. So we called this LEAP to deliver those two key insights for operators: life extension and asset management. And LEAP is supported by an innovative monitoring system. Although we can work with kind of legacy, more traditional setups, like shown on the left with strain gauges, the most robust and reliable insights can be achieved by moving to cutting-edge load monitoring strategies. And by moving away from strain gauge-based monitoring, we eliminate those key problems with gauges installed in challenging locations to repair in place. So gauges below the waterline, or in locations which are inaccessible in service, to instrumentation which is only installed above the waterline. So you can see in the center a strain gauge at the interface, or the point where the tower connects to the foundation. And then we install accelerometers at a few locations in the tower, and this allows us to capture the motion of the structure in real time. And we also make use of the SCADA data, so that's the operational data recorded at each location in a wind farm. So that allows us to understand what the wind climate is in terms of wind speed, wind direction, and also operational conditions of the turbine, whether it's operating or idling. And our approach is set up in a way that the data produced, which is significant, can be transmitted reliably to a location for analysis. It's accessible at any time, and also allows seamless ongoing assessment as environmental and operational data changes. So the key point here is being able to understand the load in the structure at any elevation, and the basis of this monitoring approach is that the load field of the combined structure can be described as a function of its displacement field. So we use a numerical technique where we can combine or use a numerical model, which is shown in the center, to characterize the dynamic behavior of the structure under different modes. So for a monopile structure, it's quite simple. You can imagine that for more complex structures, this is more complicated. And we can use the monitored data to essentially tune the measured response to match the numerical representation. It's a little bit more complicated than that, but it allows us to then determine load time histories at any part of the structure based on only monitoring at certain locations above the waterline. And wind farms contain, many locations, many different foundations, and to install even this reduced monitoring arrangement on every single one would be quite prohibitive. So we've developed an approach that works on a sort of fleet leader approach. So we can select a number of locations which can be considered to govern the fatigue load at other locations. And then we can extrapolate the load that we measure conservatively to the sort of sub-locations in a cluster to account for local water depth, the wind climate, and also the turbine operation. And that data comes from the SCADA or operational data stream. And we also account for other effects, so long-term changes in wind direction and also damaging events such as turbines idling or start-stop events for maintenance or component repair. And these are things that are often exceeded compared to design assumptions, can be difficult to predict and can be very damaging. So in terms of their effect on fatigue life. The approach has been extensively validated. It may sound quite complicated. You're making quite bold predictions based on a small amount of data. We had the opportunity to work on a UK wind farm, which had a number of strain gauges that were functioning at the mudline, which is a critical location often for fatigue load in offshore wind foundations. And we were therefore able to predict the load response at this mudline elevation using our above waterline monitoring system, and therefore compare predicted response measured from data collected some 40 meters higher to the true value. And I won't describe in detail what these figures show, but essentially they compare those results across a range of loading regimes, so different sea states and production operational states, and you can see that the results are line on line almost, so very high accuracy. And on the right hand side is showing the correlation over some 200 days of monitored data. And it's not just about measuring the load. The in-service low profile itself can provide a lot of margin, but there are also other factors that influence fatigue life. Things like scour of foundations. This applies to offshore wind foundations, but also any kind of offshore structure, seabed mobility, which can change the way the foundation interacts with the soil and decreasing the fatigue life by increasing load. And we can automatically assess this effect using the latest industry guidance. We can also implement calibration and sensor failure into the data analysis. So when you're kind of moving to a monitored data-based approach to operating your asset, it's important to be able to have confidence in the data. So being able to demonstrate calibration, particularly without having to visit the asset, is very valuable. And there's also a lot you can do with all this data. So something that we've been looking at is whether we can use the data collected to make predictions about other integrity risks. So for example, measuring the natural frequency of the structure and using that to determine whether scour is developing in a wind farm, and we've been able to demonstrate that and correlate to measured data at a UK wind farm. And just to sort of wrap this section up, ultimately the value of fatigue reassessment using monitored loads is that measured load can be demonstrated to be lower than design assumptions or from other reassessment techniques that do not rely on monitored data. And this can demonstrate an increase in fatigue life, or it can mitigate in-service integrity risks which would have reduced the fatigue life, such as corrosion. So in this figure, this is showing the fatigue, or a representative fatigue load profile going down the foundation of a UK wind farm. So on the black line on the right hand side is the design fatigue moment that was used to determine the original design life. And then the red line is showing what you might achieve by a kind of typical reassessment approach. So kind of rerunning your design stage analysis, but tuning certain parameters to reflect better the in-service condition. So you might update the natural frequency to measure what you see in reality, but not actually replacing all of your data inputs with real measured data. And then the green line indicates what you can achieve by loads monitoring. So this is what our LEAP platform has produced for this farm, and it shows that a factor of 2 increase or decrease, sorry, in the fatigue load from the design assumptions. This is really significant, especially as fatigue life scales as a sort of power law with load. So the effect on life is even more significant. So just to wrap up and sort of bring this into reality, I wanted to provide just a case study, which is looking at how foundation integrity is being managed with a view to life extension at the London Array wind farm. London Array is one of the world's largest wind farms by number of turbines, 175 locations, and therefore it has quite a significant asset management burden. And it's also a relatively early UK farm. It's a round 1 farm, so it was designed over 10 years ago and is now approaching sort of mid-life. Just a little bit on how we deployed the system at London Array. We started with what we call a discovery phase. I think it's very easy with monitored data approaches to kind of throw the book at it and install lots and lots of sensors and capture lots and lots of data, which becomes very difficult to manage. And what we achieved through this phase was talking to the users, the owners, the managers, the integrity engineers, and actually understanding what they needed, what their pain points were, what their requirements were, and what they wanted to achieve from the system. And from that, we tailored our system to what they needed. That then led to design and commissioning of the condition monitoring system, and also included calibration. We then collect data for sort of 1 or 2 years. This is typically what you need to be able to give useful insights, allow the data you've collected to converge on a representative value. You need to see a few winters or at least 1 winter of data to capture high wind speed storm events. And then we developed, the interface, the way of reporting the data to the client. At London Array, they've got this innovative monitoring system that I described, so sensors above the waterline, very easy to maintain, to repair if it needs to be. And it's installed at a small number of locations. So of those 175 locations, we don't need to install anywhere near all of them, not even 5%. And we can then extrapolate across the wind farm to other locations, but still remaining conservative. We can also incorporate inspection data, so in-service scour, corrosion inspections, and feed that into the model so that we've got a more data-driven representative view of the true asset condition. And also the way we've sort of arranged this platform, the asset integrity engineers actually have access to the platform in-house. It means they can run sensitivity studies. They can see what the effect of increasing scour, so erosion of the seabed at certain foundations, might have on the fatigue life. And what that allows them to do is to identify high-risk locations, and then they can use that to inform an ongoing inspection strategy. So they might decide that they can maybe inspect some locations less because they're low risk, and that means that you can move to a more risk-based way of inspecting and managing your assets. So finally, kind of the final outcome was that at London Array, the critical foundations, the critical welds with low fatigue lives, were predicted to increase by a factor of 3 using this approach relative to the latest in-service assessments. That's without loads monitoring, and that obviously it gives you a lot of more flexibility in terms of how you manage the asset, and also the potential for extending the life of the asset as it approaches the end of its design life. It also allows you to mitigate certain integrity risks that have developed at the farm, and it can also be used looking forward to even exploit that increase in fatigue life to look at turbine upgrades. So can you extract more power, more utilization from the asset, which is obviously very valuable to operators. Just to finish off, as I'm approaching nearly 30 minutes, I just wanted to touch on the fact that these techniques can be applied to other structures. Really, any structure that is subjected to dynamic loads where fatigue is a concern can make use of loads monitoring and fatigue reassessment to demonstrate a range of value, whether that's extending the life, justifying continued operation in light of defects or cracks being found or corrosion, but also to support repair or maintenance strategy. So structures that we do get involved in at Arup outside of offshore wind are other offshore structures, so jacket type foundations. These are still certainly fatigue sensitive. They are much more complex in terms of their geometry and their loading. And this means that monitoring is more complicated. You do need more sensors, and often it does need to be combined with numerical approaches, because you can't break down the structure sufficiently to rely on a small number of sensors alone. But there is significant value in life extension, but also for aging assets which may not have been designed for decommissioning. It provides a way of justifying continued safe operation, or understanding the effects of decommissioning, deconstruction on these assets. Bridges are another type of structure which are subject to fatigue loads, so wind and traffic loads. The fatigue of steel decks and also the monitoring of cables is very high value. Something we typically see is that a key design assumption that is exceeded is traffic loading. So it was very difficult to predict how much traffic there would be and how heavy it would be 10, 20 years ago. So we see many existing bridges where the fatigue life has been used up early by excessive traffic, and we can use monitoring to reassess the fatigue life based on measured loads, and we can either demonstrate life extension or, more commonly, design strengthening schemes based on in-service loading. And finally, there are more novel structures that are still subjected to cyclic loads, so perhaps things like cranes, which have repeated operational loading, are still subjected to fatigue. It may not be something that is commonly considered in the design of these structures, and therefore monitoring can allow you to understand the effect that your operations have on structural integrity and be able to operate them more safely, or ensure that inspection and maintenance is adequate to provide sufficient reliability. That's kind of all I had prepared. I hope that was interesting. It's obviously quite a complex topic, and I did have to skim over a few things, but I'm happy to take any questions if there are any.
Thanks very much, Robin. That was very interesting. You covered quite a lot there. So, as I originally said, this is an Aberdeen area committee presentation. It was actually Tegwin who put this one together, Tegwin Northampton. She's done a great job bringing it all together here. So if you go into the Aberdeen website or onto LinkedIn, you'll see all our events. You'll see this one here. The next event, which is coming up in Aberdeen, is actually at Robert Gordon's University tomorrow night. It's at 6:30 or 6 o'clock, I think it is now. Hydrogen storage and utilisation. It's the Ballymundford P2X feed development. And it's all about how we are doing a feed study to look at exploring hydrogen storage and utilisation. So a really good topic to bring on for the next Aberdeen event. So other than that, I'd like to thank once more time Robin, and thank you everyone for attending. And we'll finish off the presentation and event there. Thank you very much.
Thanks for having me.
Thanks, Robin.